Okay, so it is my pleasure to introduce to you Philip Wadler, who is one of the co-designers of the Haskell programming language, who brought generics to Java, who did extensive work communicating the ideas of monads to the programming world. So much stuff. I can't really sum it up, but he is here tonight to talk to us about category theory for hackers.
Good evening. Can you hear me?
Yes. Did you use the microphone?
Yeah.
Can I use the microphone?
Let's try that.
Can you hear me?
Yes.
Okay. Great. Let's see. I'll need to do that sometimes, so I guess I'll stand here. Thank you for coming tonight. Normally I know that I've got an audience of developers, but after being taken around this space, for all I know you are all dressmakers. And I have this hidden hope that one of you is going to sneak off during my talk, do a laser cut commuting diagram and present it to me at the end of the talk. I don't know if that will happen, but this is the sort of space where it could happen. So I just want to check on my audience. How many of you actually are hackers in the sense of people who write code for computers? Pretty much all of you. You didn't raise your hand though. So you're not.
I'm a mathematician and a cognitive scientist.
You're a cognitive scientist. Okay, cool. And what do you do?
I'm a learning science analyst.
Learning science analyst. Okay. I'm sure category theory has applications in both those areas.
Yes.
Well, I'm going to be talking about the applications of category theory to computing. And the reason I'm doing this is that several of the ideas I've worked on, most notably the stuff with monads that Daryl mentioned, came from category theory. So my job was to explain it without using category theory. But if it hadn't been for the people who knew category theory and used it to develop this, I never would have found it. Once you found it, you don't need any category theory to do it. But category theory is a great help in finding it. Category theory reveals, I'll use a fancy phrase, deep underlying structure of things. And in particular, what I want to do today is to show you three, right? The three most important data structures in computing: the product, the sum, and the exponential. And by the time you're done, you will have realized that if you don't know it already, you will know that these are three things that you're familiar with, that you've seen before. But because they have such straightforward definitions in category theory, that gives us a lot of understanding that these are actually fairly deep and fundamental things. So that's the idea. It will take about an hour to do so. Is that amount of time okay with people? Okay. And I need your help. Right? My problem with teaching this stuff is I know it way too well. So I will just say something and assume that that's abundantly clear to everybody, and it won't be. So your job is to please ask questions if you don't understand anything. Are there any questions? Not yet. Okay. Very often people are shy about asking questions. You know, they'll be sitting there and they'll say, monads. He's talking about monads. I've never heard of monads. Maybe I should ask. No, I'll look stupid. So what you do is you turn to the person next to you and you say, do you know what a monad is? Well, you whisper it, right? One of two things will happen, right? They will give you a withering look and say, of course, don't you? Right? But that's very rare, right? What's much more likely is they'll say, no, I don't know what monads are either. I'm lost. And at that point, you know it's safe to ask a question. Okay, are there any questions? Yes?
One thing you can also do is point to something you don't like and say, my friend wants to know what monad is.
Okay, that one works too. Okay, nobody's at, yes?
I think my friend has a question. I think he was wondering what monads were.
I'm sorry about this. I think I'm sorry.
Right, so the question is that his friend was wondering what monads were, and he'd like to know. So, in fact, at one point you will see a monad during this talk, but it will sort of whip by. Monads are a method used for structuring things when writing certain kinds of programs. The idea originally came from category theory. It was applied by Eugenio Moggi to semantics of programs, and then I looked at it and said, oh, we can actually use that for structuring functional programs. So it's used for a wide variety of things, including any interaction you want with the real world in Haskell is done via a monad these days. It used to be done a different way, and then we started doing it with monads. So I won't go further than that. If you want to know more, it's easy to go and look it up. But it's an example where category theory gave us something really powerful for structuring lots of different kinds of computations. So it lets you manage error handling or updatable state or doing input-output or a number of other things. Some people call it a programmable semicolon. I'll leave it at that. But thank you. That was the question I was hoping for. Now I know you're awake and that you're actually going to pay attention and help by asking questions. Okay, so are you ready to learn the 3 most important data structures in computing?
Yeah!
Well, you're not, because before you learn about them, you have to learn what a category is. So we'll do that first. A category is very simple. It consists of blue thingies, black thingies, and red thingies. The blue thingies are called objects. The black thingies that look like pointy arrows are called arrows. And the red thingies are just labels on the arrows. They are the names of the arrows. So sort of a black thingy and a red thingy together is an arrow. Question?
Yes, between F and G, is that the letter I or is that a semicolon?
Ah, very good question. So here I've written F semicolon G. That's a semicolon, not an I. Thank you. Yeah, no, it's not fig. So here the particular case we have here is we've got 3 objects, A, B, and C. F is an arrow between A and B. G is an arrow between B and C. And category theory just lets you, it has a very minimal amount of structure that you start with, which is just that you have arrows and then you've got only one thing you can do with the arrows, which is compose them. So, well, if I've got an arrow from A to B and an arrow from B to C, I can create an arrow going from A to C, which is written F semicolon G. Sometimes that's written G circle F, just to give people a headache from reading things backwards. And then the one other thing we can do is, okay, we can string together a bunch of things. So we can combine 1 or 2 or 3 or 4. If you're a computer scientist, you know that counting starts at 0. So what would be composing 0 things together? Well, that's starting at A and going back to A. So that's the identity arrow for A. And for each object, there's a corresponding identity arrow. So that's it. So, yeah, question?
Does that imply then that every possible value in A has to be acceptable to the function F and create a valid B, and likewise?
Okay, so you asked, does this mean that every value of A must be acceptable to the function F? Not quite, because categories are just slightly more general than that. Right? I've just said this is an object A. So the obvious model that you probably have in mind is A is a set of things, and B is a set of things, and then F is a function that takes elements of A to elements of B. So that is indeed an example of a category, but there are some categories so general that you can't talk about are there things in A. So if there were things in A, what you said is exactly right, but you don't necessarily even have things in A. Good question. Okay. Any other questions? So, as I said, one model is these things are sets. Another model is these things are types in a programming language. And F is a function or method in the programming language that accepts values of type A and returns values of type B. That would be another example where F and D must act on every value of type A. You might have these things be more general. They might be things like algebraic structures, like a group, and then F would be what's called a morphism, or a homomorphism between the groups that preserves all the group structure. So there are lots and lots of different examples of these things. And the point is just we have very little structure here, even less structure than you have in set theory. And it turns out that's a good thing, because having even less structure makes it easier to do things, in that you've got very few components to build with. So very often they're just a couple of different ways of doing things. And that's typically what happens in category theory. They're just a couple of different ways of doing things, and you say, and they're all equal. And then you've defined something. Okay? That's how category theory works. Roughly speaking, right, many of you are familiar with programming. Many of you are familiar with set theory. What category theory is about is making that stuff so general that something that's very familiar and obvious to you becomes difficult to understand. Right? That's really what category theory is about. It's the easy, obvious stuff made hard. That was the phrase I repeated to myself all the time I was learning category theory. So don't worry if it seems hard at first. That's the goal. So of course that's facetious, right? What is really the goal? To strip away so much that these become very general and applicable in very many situations. And that you can pull out the essence of what's going on in an easy way. So then composition satisfies a very small, obvious number of properties. So the line on the bottom says, if I compose F with G, and then compose that with H, that's exactly the same as composing F with G composed with H. Right, so it's just two different ways of parenthesizing. No, that doesn't work too well, does it? It's just two different ways of parenthesizing the same thing. And then the other obvious thing is to say, okay, in the zero case, if you're just going from A to itself and you compose that with F, well, that's really just the same as doing F alone. So it just says that identity is, in fact, what's called the identity element of the semicolon operator. Okay, so if we do identity followed by F, it's the same as F, and that's the same as F followed by identity. Many of you will have seen things like that before, I expect. Okay, so how many people this looks completely obvious and straightforward and you're all bored? Okay, small number of you. Okay, you now know enough category theory to get your first data structure. Okay, and this is the product. So let me decompose this diagram. So if you say this category has products, what you're saying is the following. Or, actually no, I'll back off a little bit. We'll just define something called the product of A and B. So, A is an object, B is an object. We're saying for A, there is another object which we're going to call A times B. And this has the following properties. First of all, there's an arrow from A times B to A. It is called first. Second of all, there's an arrow from A times B to B. It is called second. Third, for every other object C, if I have an arrow F from C to A and an arrow G from C to B, then there exists a unique, so there exists a unique, in category theory is written dash dash dash. So this dashed line is telling us that this FG arrow is the unique such arrow. It exists and it's the only one that exists. So this says there exists an arrow FG going from C to A times B. And then there's one other thing you need to know about these diagrams. They're called commuting diagrams because if you can get to two places in different ways, they must be equal. So what this tells us is, okay, F goes from C to A, but I can also get from C to A by using FG to go from C to A times B, and then using first to go from A times B to A. So this tells me that FG followed by first is the same as F. And the other half of it is telling us that fg followed by second is the same as g. So we can just write those two equations down. But then I also said this thing that exists is the unique such thing. So that gives us another equation, a conditional equation. It says, okay, let h, so what does it mean for it to be unique? Well, let's say h is another arrow that satisfies exactly the same properties. So that means h goes from c to a times b, and that h followed by first is the same as f, and h followed by second is the same as g. So I've written this out here as two things above a line, and this is just a conditional equation. It says if all the equations above the line holds, then the equation below the line holds. So this says, okay, if h followed by first is f, and h followed by second is g, then h is the same as bracket fg. That's it. That already is enough to tell us things. So for instance, right, I can pick f and g to be any f and g I want. So I'll pick the most trivial possible case that makes this true. I will pick f to be h followed by first. And I will pick g to be h followed by second. So then trivially, of course, we have h followed by first is h followed by first. Yep, that's true. And h followed by second is equal to h followed by second. Yep, that's true. So what do we get? We get h is equal to f paired with g, which in this case is h followed by first paired with h followed by second. And then that's kind of interesting, right? Because it tells us every possible arrow from C to, right, we assume no interesting properties of h. It was just an arrow from C to a times b. So this tells us every arrow from C to a times b can be rewritten in bracket form. So in fact, the only arrows from C to a times b are these bracket things. So that's the first thing that followed out of the categorical definition. So how many people have cottoned on to what a times b is, and what this bracket construct is, and what first and second are? Okay, a few of you are, good. So what is it? Sorry? Pairing. The pair, yes. Or the fancy name we use in computing is the record. And there's a name we use for this in set theory as well. Does anybody know that name?
Intersection.
Sorry?
Intersection.
Intersection. No, this is not intersection. It's not union. It's the product, indeed. And in set theory we call it, and in set theory we call it the Cartesian product. Okay. So if this is the pairing type, well, first of all, that explains why we call products, right? So let 3 be an object, and in this case I'll let it be a set. It's a set of 3 things, the letter A, the letter B, and the letter C. We can represent that in most of our programming languages. And let 2 be another set consisting of just 2 things, 0 and 1. Then what is their Cartesian product? It's just all possible ways of pairing them, right? So it's A paired with 0, A paired with 0, B paired with 0, C paired with 0, A paired with 1, B paired with 1, C paired with 1. And you can see, right, that there are 6 things here, right? The number of pairs will be equal to the size of the first set times the size of the second set. That gives us the size of the Cartesian product of those 2 sets. So that's a hint as to why we call it the product, because you get the size by multiplying things together. And then, if we go back and look at this, what do these 2 different things do? Well, given a pair, right, first extracts the first component of the pair, second extracts the second component of the pair, and what does FG do? It builds a new pair. How does it do it? So the way FG works is F takes a C to an A. So given a value in C, we apply F to it to get a value in A. And similarly, we can apply G to it to get a value in B. And then what does bracket FG do? It takes C to a pair of things. Which pair of things? Well, the first thing is the thing you got by applying F to C, and the second thing is the thing you got by applying G to C. And we're going to, later on we're going to need to do one other thing with products, which is very straightforward. So instead of bracket FG, here we've got F times G. This is a slightly different set. Here F is a function from A to C, as before, but G is an arrow from B to D. And then we're creating an arrow going from A times B to C times D. So going from a product to a product. And the way we get here, of course, is we'll take out the first component of A times B, apply F to it to get C, and we'll take out the second component and apply G to it to get the D. And that's exactly what this says we're doing. So this is the obvious way, given something going from A to C and something going from B to D, to go from A times B to C times D. Any questions about that? So here is where the category theory really helps us out. We can summarize all that in just one line. And here's the line. So curly C is the name of our category, whatever category we're working with. And what we're saying to describe a product is we're saying, what are all the arrows from an arbitrary object C to a product A times B? Well, they're in one-to-one correspondence with having two things, an arrow from C to A and an arrow from C to B. Right, that's what we said. How do you get an arrow from C to A times B? Well, it's a pair of things. One is an arrow from C to A, and one is an arrow from C to B. So we're just saying the arrows from C to A times B are in one-to-one correspondence with having an arrow from C to A and an arrow from C to B. So everything we've learned as the definition of product can just be summarized in that one line. Is that clear enough? We'll make use of that later. So let's see this actually written out in a programming language. So here it is written out in Java. Some people consider Java to be a programming language. So what is it to have the product of A and B? Well, it just says, right, we've got a class that's got two fields. We have the field first of type A and a field second of type B. And, right, a constructor just initializes those two fields. And then we've got two operations, get first, which extracts the first field, and get second, which extracts the second field. And then to use that, we could do something like build up an integer string pair by applying product to 1 and the integer 1 and the string 2. And then to get the things out, we would use get first to extract the first component and get second to extract the second component. So that's what it looks like in Java. How many people use Java or know Java a bit? Right, fair number of you. And how many people use or know Haskell a bit? Wow, almost an equal number. Cool audience. So in Haskell it's slightly simpler. We can use a bigger font. In fact, in Haskell it's much simpler, right, because the notion of pairs is built in. Right, you just use round brackets. But if you were defining it in Haskell, you'd say I've got a product of A and B, and that's built with the pair constructor and has two components, an A and a B, of type A and B. And first is the name of the function that extracts the first component, and second is the name of the function that extracts the second component. And then to do the same thing as before, we do pair of 1 and 2 to build up a pair. And we would just apply first to pair to extract the first component, and second to pair to extract the second component. That's it. You now know your first basic data structure. Are you ready for your second data structure? So our second data structure is the sum. So we get another funny diagram. And what does this one tell us? So again, we're given an object A and an object B, and we're told, okay, there's another object, A plus B. And furthermore, there's an arrow called left going from A into A plus B. Remember, first went from A times B to A. So this one goes the other way. And there's an arrow right going from B into A plus B. And then we're saying, given an arrow F from A to C, and an arrow G from B to C, we get an arrow square bracket FG going from A plus B to C. And again, this is a commuting diagram, so we're saying a bunch of things, right? We're saying that left followed by bracket FG is the same as F, and right followed by bracket FG is the same as G, and FG is unique. Let's do all these things, right? So left followed by FG is F, right followed by FG is G, and it's unique. So that means if we've got an H going from A plus B to C, such that left followed by H is F, la la, and right followed by H is G, la la, then we know that H is the same as FG. And again, by picking F and G to be trivial to make that true, we can show that any H is equal to left H bracketed with right H. So again, any arrow from A plus B to C is of the form square brackets of two things. So how many people have guessed what data structure the sum is? Okay, so what is it? It's sometimes called the union. In set theory, actually, we would call it the disjoint union, because we don't want any overlap between A and B.
I didn't mean like set theoretical
Union types in, say, C, yeah. It's also sometimes called record variance. Does anybody else have a favorite name for this sort of thing?
Tag union.
Sorry?
Tag union.
Tagged union, yes, that would be another name.
Some
The sum type, that's a good name for it.
either.
And in Haskell, it's called the either type. Sorry? Right, and if you're really categorical, it's called the co-product. For a reason that we'll explain later. Sorry? Each of. Sometimes people call it each of, yes. So, and again, you can see why it's called the sum type, right? What are the ways of building something of type 3 plus 2? It's either left of A, or left of B, or left of C, or right of 0, or right of 1. I'm pointing at this and you can't see them pointing. There we go. And notice that in general, right, it will be size of the type on the left plus size of the type on the right gives you the size of the sum. So again, that's a hint as to why it's called the sum type, because we just add together the sizes of the two. So let's have a look at this in Java again. It's very easy. Oh, no, there's one more thing to say first, sorry. And again, everything we said can be summarized very compactly, right? Because what have we said now? We've said, what are the set of arrows from A plus B to C? Well, they're in one-to-one correspondence with having an arrow from A to C and an arrow from B to C. Are there any questions about that? I got a really good question earlier today when somebody looked at it and said, wait a minute, why is that times? Why isn't it plus? Right? We use times to define times. Surely we should use plus to define plus. No, it's still a times because we're saying, no, it's in correspondence with having a pair of these arrows, right? You have an arrow from A to C and an arrow from B to C. You must have both of them. Right? And by the way, right, what is the interpretation of each of these things? So left takes an A and turns it into a member of the sum type. And right does the same. And then what does bracket FG do? How does that work? Yeah?
It uses whichever right happens to be and the corresponding morphism to produce a C.
Right. And there's a name we often give to these things in computing. Right? it's a case expression, or it's a switch expression. It's something that looks at what we've got and chooses accordingly. So FG says, well, let me look at the thing I've got. If it was built with left, then I'll apply F to the thing that left was applied to. So that means I'll use this F. If it was built with right, I'll apply G to it. So it's a case expression. We're choosing one or the other, which of F and G to do, depending on what was I given something in A or something in B. Right? And so the property of the sum type is, of course, everything in it either came from A or came from a B. Yes?
Okay, so I noticed in the product version, FG in the middle of the arrows uses the angle bracket, this one uses the square bracket. Is that just a convention talking about the sums?
So, right, the convention is we use angle brackets for products and square brackets for sums. It's just a convention. I could have said product evented bracket and summy bracket. Does that answer your question?
Yeah, thanks.
Okay.
So that's just an easy way when people look at it, they know that they know right away you need sums and not something else.
Well, right, we clearly they're very different things, so we need some notation to distinguish them. And in category theory, the way they distinguish them is writing angle brackets around the producty ones and square brackets around the summy ones.
So does the last one use the squiggly brackets?
Sorry?
There are three ones, right? There's sums, there's products, and there's the third one. The third one uses squiggly brackets.
The third, so you might guess the third one is curly brackets. Interestingly, no. But good guess. Maybe we should do that. Okay, but anyhow, so arrows from A plus B to C are in one-to-one correspondence with having an arrow from A to C and an arrow from B to C. So now we can look at what this looks like in Java, and it's really straightforward as long as you write really small. I had various comments after the first talk today. People said, no, that's too small. People in the back couldn't see it. Well, yes, sorry. That's Java's fault, not mine. So what have we got here? We've got an interface, sum of A and B, and it just has one method called case expert, which has two arguments. A function from A to C called F, and a function from B to C called G. So you can see where those are coming from. And then we've got two classes that implement this interface. There's a class called left that of AB that implements sum of AB. And what does it have? Well, it has a private field of type A, we'll call it X. And then the constructor, left, just sets the X field. Notice there's only an X field, right? There's no field of type B, because it's a sum type. And then the case expert takes an F and a G, and it applies F to X. It says, okay, I'm on the left, so I'm going to ignore G and apply F. The case expression takes both, and then says, no, this one's a left one, so I'll just apply F. And then writes the same way around, except now we've got a private field of type B called Y, and we build up right, and then the case expression applies G to Y rather than applying F to X. And so you have to do that, right? This is the only thing you could do. You couldn't use G because you don't have a B around to use here, and you couldn't use F because you don't have an A around to use here. Yeah?
The return specifier for case expert, bracket C, what does that represent?
Oh, here.
With that,
this just says it has that type for all type C. That's how you do generic types in Java.
okay.
So this just means for all type C, this has this type.
I see.
Right, notice A and B are fixed up here. And then here we're saying, and it works for any C you'd like.
Oh, I see.
You see, ha ha ha. Okay, and then the way we would use this is, let's build a new class called arint that extends, that is an instance of sum instantiate to string and integer. So an arrant is either a string or an integer, and that is the string would be an error message. So, for instance, if I make new left of error, that would be an error message of type arrant. But if I do new right of the number 1, then that's a way of representing 1 in this arrant type. And then how would I add two arrants? So what we'll do is we'll look at the first one using case expert, and it'll either be on the left or the right. So if it's left, its argument is an error message E, and we just return left of E unchanged. Otherwise it's M. If it's M, so that's a number, then we look at the thing on the right, which I've called that. And again, we pull that apart with the case expression. Either it's an error, in which case again we return an error, or it's a number n, and then we'll return right of m plus n. So this just takes two arrants. If they're both ints, it adds them together and returns that int. And if either one was an error, it returns the corresponding error message. And notice it's biased to the left. So if I add two things that are errors, it'll give me the first error rather than the second error. And then here's an example of 1 added to error, which of course would just be the same as error. If I did 1 added to 1, that would be right of 2. Is that clear enough? Okay, and then again, we could do this in Haskell, but in Haskell we get to use a bigger font. And so we say the type sum of A and B is either left of A or right of B. And in fact, this is actually in the Haskell standard prelude, except sum is called either. And left is called left, and right is called right. And then to do the same example, we just define arrant to be the sum of string and int, and then error would be left of error, 1 would be right of 1, and then the way add works is it takes two arrants and gives us an arrant, and we look at if the first one is a left of an E, we return left of E. If the second one is a left of E, we return left of E. And which of these fires is determined by the order in which we write down the equations. And then if they're both right, if we've got a right of M and a right of N, we just return right of M plus N. And then test would be add 1 to error, as before. Okay. So does that help clarify what sum types are and how the bracketed FG thing is just a case expression? Okay? So that's the second data type. You're now ready for the third, exponentials. So I mentioned that category theory is stuff you know made difficult, right? So we took the record type or the pair type that you're really familiar with and we called it product. And we take the record variant or tag union type that you used to and we call it sum. And what an exponential is it's just the function type, but we're going to call it exponentials. And basically what's going on here is, right, I've already talked about arrows from A to B. Now in set theory, you can think of the set of functions from A to B. So in category theory, that's not guaranteed, right? There's not necessarily an object that corresponds to all the possible arrows from A to B. But sometimes there is. Right? All of these things are extra bits of structure you can add to a category. So if I tell you, here's a category, right? All you know is that it's got arrows and objects and you can compose them and you've got identity arrows. And that's it. So, right, if you're at a party, right, and you bump into somebody and they say, oh, you know, what are you? Oh, I'm a category, right? What kind of questions can you ask? Well, you can ask questions like, oh, do you have products? And it might say, why, yes. For every object, pair of objects A and B and B, there is also an object A times B, which is the product of A and B. Or you might say, do you have sums? Or you might say, do you have exponentials? So if it has exponentials, that means that there is an object. For every pair of objects, there's another object that represents the functions, or the arrows, from the first object to the second object. And we just write the object that represents all the arrows from A to B as A fat arrow b. So now we want to characterize that, and the way of characterizing it is really bizarre. But this is the easiest way anybody's ever found of characterizing the function space. So we'll talk about functions from two things to be. So we build exponentials on top of products, just like exponentials in real life are repeated products. So we're going to say given an arrow from c times a to b, there exists an arrow from c to a fat arrow b. Right, so here a fat arrow b is another object. So we've got an arrow from the object c to the object a fat arrow b. And its name is curry f. And what are we saying here? Well, the first thing we're saying is, okay, things in a arrow b, a fat arrow b, represent arrows from a to b. So we're saying, okay, given an arrow from a to b, and given something in a, what can you do? You can apply that arrow to that thing in a and get something in b. So this is this arrow apply. So just like we said we've got first and second, or left and right, we're saying we have an apply that goes from a fat arrow b times a to b. And that just says, right, take the arrow in the first thing and apply it to the second arrow, to the value in the second arrow. And then what we're saying here for the commuting diagram is, so this line should be half dotted. I didn't know how to half dot a line. So the first bit of it always exists. Right, so here we're using this times that we defined before. Just as, okay, we're going from c times a to b times a. And how do we do that? We'll leave a alone and apply curry f to go from c to a fat arrow b. And we say, well, if you start with c times a, you leave a alone, you go from c to a fat arrow b via curry f, that gives you an a fat arrow b times an a, and then you use apply to get to a b. That's just the same as if you took c times a and went via f to b directly. And then we also have things guaranteeing it's unique. So I write down other things with h, but I'm not going to bother to do that this time. But it follows the same pattern. So that's exactly what the commuting diagram is telling us. And why is it called the exponential? Well, how many different ways are there of going from a set of size 2 to a set of size 3? Well, there are 3 squared. 3 raised to the 2 power. So you just flip these two around and take an exponent. Right? And what are the 3 squared things here? Well, it's 0 maps to a and 1 maps to a, or 0 maps to a and 1 maps to b, or 0 maps to a and 1 maps to c, or 0 maps to b and 1 maps to a, or 0 maps to b and 1 maps to b, or are you bored yet? I'm bored. I'm not going to do the other 4. But you can see that there are a total of 9 of them. And in general, for finite sets, the number of different functions from the first set to the second set is just the size of the second set raised to the power of the size of the first set. For finite functions, that's always true. So, and then what are we saying? Well, we're saying, again, in very compact form, what is the set of the arrows from C to A fat arrow B are in one-to-one correspondence with the arrows from C times A to B. So here we have an A arrow B. Here we have C on the left and A arrow B on the right. Here we have C times A on the left and B on the right. So an A arrow here turns into a times A here. So again, we can do this in Java, right? We'll define, so Java actually has a function types built in now. It has ways of writing down functions, which are called lambda expressions, built in. So we've got something that takes an integer n and returns a function from integers to integers. So this integer is our type C, this is our type A, this is our type B. And which function is it? It's the one that, given an integer x, returns x with n added to it. So then, for instance, I could define increment, which is a function from integers to integers, to being add of 1. So it's the function that adds 1 to things. Right? Add of 2 would be the function that adds 2 to things, and so on. And then I could do 3 by taking increment and applying it to 2. So notice that functions are actually built into Java, so we can actually use a bigger font to write this down. If functions weren't built in, we would have to use a smaller font again. Right? Lambda calculus was invented in the 1930s. Java finally caught up, right, by about 2015. And we can do the same thing at Haskell, also in a big font. Right, so add takes an integer, n, and returns a function from integers to integers. So again, this is the function lambda x goes to, well, I should have said x plus n to make it look like the other one. But here I said n plus x. And this backslash is just Haskell for what Alonzo Church wrote as lambda. So this just means, you might pronounce this lambda x, goes to n plus x, and it's just the function that given x returns n plus x. Yes?
And in what year did Haskell implement the lambda?
Good point. Also a lot later than Church. But we designed Haskell in 87 was when we started to do it. And Haskell followed other languages which were defined in the 60s and 70s and the earlier 80s. So there are lots of things that influence this, including Lisp, which of course used the keyword lambda to stand for exactly this, and that's because John McCarthy was a student of Alonzo Church. In fact, when they were saying, oh, let's use S expressions to write down our programs, what shall we call the thing that stands for a function? McCarthy said, oh wait, that's in my notes somewhere, and he went back and looked it up and said, oh, we'll call it lambda, but they used dynamic binding. If he'd paid attention to the way lambda calculus was defined, they would have used static binding from the start, lexical binding from the start. But they didn't get that right in Lisp. It wasn't until Scheme came along about 10 or 15 years later that they did properly with lexical binding. So that was a really good question, thank you. Anyhow, so this is very straightforward, and then increment is just add applied to 1, and then 3 would just be increment applied to 2. And in fact, in Haskell, I'll get to your question in a moment, in Haskell, the whole notion of currying is built in. It's actually how we define multi-argument functions. So if you want to define add that takes 2 arguments, n and x, and returns n plus x, well, its type is just give me an integer and return a function that taken an integer returns an integer. So you just define functions of 2 things in terms of a function of one thing that returns a function of the other thing. And then so increment, again, is just add of 1, and 3 is just increment of 2 still. So this idea is actually built into Haskell. You had a question? Oh no, I made you forget your question. He has a question.
Do you remember he asked me? It was what's lexical binding?
Oh, that's a very good question. Right, what's the difference between dynamic binding and lexical binding? Dynamic binding is wrong and lexical binding is right. And what this actually means is in dynamic binding, if you refer to x within the body of a lambda expression, and it's not if you refer to n, let's go back for a moment. Right, which n is this when you refer to n? Under lexical binding, it's the lexically and scoping n, which is right here. In dynamic binding, if I said, before I said add 1, I said let n equal 3 in add of 1, it wouldn't return, let's try this one. If I said 3 is increment of 2, but I did it in a scope where I'd say, well, no, let n equal 3 in increment of 2. Instead of returning 3, it would return 5. It would use the dynamically closest value of n rather than the lexically nearest value of n. So it's wrong. I know people that refer to the original definition of Lisp as just a bug, but it took lots of very clever computer scientists about, I started doing, I'm old enough, I started doing computing before people had this problem sorted out. And Lisp still used dynamic scoping, and they had something called the fun arg problem, which meant that here it would return 5 rather than 3, and you really wanted 3. It's called the fun arg problem. Eventually they solved it by using lexical scoping. It took about 15 years to get that sorted out.
Funar?
Yes?
What is that?
That was just the name of the problem.
Oh. Where did it come from?
It came from fun, function, and argument. It did not come from the fact that it was fun. It did sort of come from the fact that when you looked at it, you went, argh!
I just want to add that dynamic binding is the reason you have headaches with this in JavaScript.
Oh yeah, right. Good example.
Okay, good question, thank you. Okay, so that's all with exponentials. So we're done. You have now seen the 3 most important data structures in computing: the product, the sum, and the exponential. And you could come up with these without category theory. We did. But category theory tells you something about just how fundamental these 3 things are. Right? And the category theory gives you a lot of generality. So one thing I haven't referred to is another possibility for instantiating these things is that you take objects to be formulas in logic and arrows to be proof that the first formula implies the second formula, that you can derive the first formula given the second formula. And then it turns out products correspond to conjunction, logical and, sums correspond to disjunction, logical or, and fat arrow corresponds to implication. So the basic ideas in logic also show up here. So this is the 3 fundamental data structures in computing, and also the 3 fundamental ways of combining things in logic. So, right, category theory pares things down, right? You have very little structure originally. Right? All you've got is objects and arrows and composition and identity, and that's it. But by paring things down, certain things become clear that wouldn't be clear otherwise. So in set theory, you have Cartesian product, and you have disjoint union, and they're just 2 different things. Oh yeah, we've got Cartesian product and we've got disjoint union. In category theory, they are very closely related. As somebody mentioned, sums are called co-products. And what the co means is that it's dual. And what does dual mean? Well, if you look at the 2 diagrams we drew, right, do you notice anything about them? They look really similar, right?
They're kind of mirror images.
They're kind of mirror images. In fact, they're exactly the same if you take every arrow in the first one and turn it around in the second one. Right? So in the first one we go from C to A, here we go from A to C. Right? We went from C to B, here we go from B to C. Here we went from A times B to A, here we go from A to A plus B.
Except for the unique arrow.
No. Here the unique arrow goes from C to A times B, here it goes from A plus B to C. They are all turned around. So there's a formal relationship between these 2, which is called duality. And you notice that when you turn the arrows around twice, you get back where you started. Right, so the dual of something is called the co-thing. So we say sums are co-products, but you could just as well say products are co-sums. Category theory joke. What does a category theorist call a cocoa nut? A nut. Very good. Right, the dual of a nut is a nut. Okay, so this I think is really cool. Yes, question?
Is there a dual exponential?
Is there a dual to the exponential? Yes. It's very weird. Nobody uses it. It doesn't show up at all. In logic, it is difference. It's called logical difference. Nobody has found a use for that data structure. So if you could do that, that would be a cool thing to do. Here's another cool thing that I wish somebody would do. Right? Given that these 2 things are duals, there ought to be some way of writing a compiler that only implements records And then from the implementation of records, you get for free the implementation of sums, because they're dual to records. There's one person actually who did it, and I'm really annoyed because today I cannot remember his name. But there's one variant of the ML programming language where they use exactly that idea. Okay, here's the other thing that comes out of this, right? We could, because there's so little to work with, everything gets pared down to basics. So we said, right, what is the essence of product? It's that every arrow from C to A times B is in one-to-one correspondence with an arrow from C to A and an arrow from C to B. What's the essence of sums? It's that every arrow from A plus B to C is in one-to-one correspondence with an arrow from A to C and an arrow from B to C. And what's the essence of exponentials? It's that every arrow from C to A, that arrow B, is in one-to-one correspondence with an arrow from C times A to B. And actually, you knew this already. Right? We've already seen that sets of arrows should be written as exponents. Right? So instead of writing the set of all arrows from C to A times B, we should write A times B raised to the C power. So let's just take this and rewrite it in that notation. Then the first equation becomes A times B raised to the C power is A to the C power times B to the C power. C to the A plus B is the same as C to the A times C to the B. And B to the A power itself raised to the C power is the same as B raised to the C times A power. And you learned all three of those equations back in high school. I'll stop there. Thank you very much. I won't stop there. There's further reading if you want it.
So shall we do questions that people have left over? If you have questions?
I'm actually on time. I think we have 5 minutes for questions.
And then you can repeat the questions for the...
I will try to repeat the questions when they're asked. So try to make them short.
Well, maybe it has to be later, but if you could go into more about what it is that would look like the dual of exponential.
Oh, okay. So the question is, what would the dual of exponential look like? I'm going to give you a facetious answer. Right? You just take that diagram and turn all the arrows around. And yes, how to make use of that, I don't know. The only place I came close to making use of it is I wrote a paper about what programming language corresponds to classical logic. So in classical logic, right, implication B, A implies B, can be understood as not A or B. And in fact, it can also, through De Morgan's laws, be understood as not of A and not B, in parentheses. And then working out what the dual is through De Morgan's laws is fairly straightforward, but it still doesn't seem very useful. So, I should at this point give you a nice intuitive explanation of what's going on. I don't have one. It makes my brain explode too.
I can see
So,
coming up if you were trying to implement like a purely functional intercal. You see what I mean? Like,
no, I didn't get your joke because I don't know.
Go to.
So sorry, I should repeat the question. So the question is, it's sort of like a purely functional intercal, but I don't know what intercal is.
Intercal, it's a joke programming language that's come from instead of go to.
Intercal
is kind of like, so if you're going to implement a purely functional intercal, then you would use the dual of the exponential operator for your mappings.
Right, so intercal is a joke language that makes things difficult, has come from instead of go to, and yes, co-exponentials might be perfect for that.
Yeah, good. I was actually going to ask if, this is sort of outside the scope of this, but if you had any opinions on extensible effects.
Do I have any opinions on extensible effects?
Yeah. Although,
Yes. My opinion is yes, they're a good idea.
Okay.
I have lots and lots of colleagues that work on this. Gordon Plotkin, who works in the office underneath mine, did the main development of algebraic effects that can be used in this way. And then Sam Lindley, who works very closely with me, is a world expert in actually trying to turn those into programming languages, and there are many other people doing this as well. And I've been sitting down with Sam and saying, ooh, this should be our next grant application for funding. So we're going to be looking at doing that. Yeah?
When you have the kind of relation between the category theory structures and the kind of arithmetical one, like, are there any other useful equivalences? Like, I know that there is something for your exponential, you actually have logarithms and certain structures you can talk about having a logarithm, like certain functions can be logarithmic. Are there any other like useful parallels that actually, in arithmetic, or by having those relations can kind of suggest interesting structures?
So I'm not familiar, so you referred to the category theoretic equivalent of logarithms, which I'm not actually familiar with, so you may know more category theory than I do. But then your question was, what other things like this are there?
Is there a good equivalent of a factorial or anything like that?
Ooh, is there an equivalent of a factorial? No, not that I know of. That doesn't mean there isn't. Are there other structures like these? Yes, there's loads, right? Category theory books get very thick. Like the next step after this sort of thing, or actually very often it's done before this, is you learn how to make categories of categories. And then you learn about things in these categories of categories, like functors, which are the arrows between categories. And then you look at a category where so first you start with your objects are categories and the arrows between them are functors. And then you make another category where the objects are functors and the arrows between them are things called natural transformations. So that's one way things go. And then another way things go is you have things called adjoints. It turns out all three of the equations I gave you correspond to things called adjoints. And adjoints are basically about having one-to-one correspondences between different sets of arrows. And these are all very powerful ways of defining things. So there's just lots and lots and lots of interesting structures that pop up. And then monads are one of these.
I would add there is a whole bunch of work on combinatorial species.
No, you can't add that there. You have to add it here.
So there's a whole bunch of work on something called combinatorial species, which is really interesting. You can look up Joyal, and they talk about things like that. So.
I don't know about combinatorial species. Aha, you have to tell me. Okay. You asked a question before. Person in the back.
You mentioned something about building sums out of products or out of record types. How would that work, or did I misunderstand?
Basically, what you can do is exploit the duality and say that what should the input to a case expression be? It's actually a record of functions. Right? If you look at the case expression, it actually took a record of functions. And you can build it on top of that. I think everybody's tired. Maybe we should wind down.
So before we end, I felt compelled to laser cut you a commuting diagram.
Oh, cool! It worked. Wow!
So let's go again.
Thank you, Joe. That's great.
Thank you, Phil.
Oh, right. I did want to leave you with one other idea, right? You should always remember, right, that when you have a hard job, you should think that this is a job for lambda calculus. Now I'll stop.
You mean the type number calculus, right?
Absolutely.
Which type system?
See me over there.
Awesome. So thank you all for coming. If you would like chips or soda or whatever, we still have chips and stuff like that over there. So yeah, I don't know if we'll have more talks like this in the future, but hopefully. Seems like a good turnout.
Great.
Thank you again, Phil. Yeah, and if you want to just like hang out and chat or hack on stuff, feel free.
To promote your Haskell class.
Oh yeah.